First of all, I'd like to take this opportunity to thank the organizers of this conference for inviting me here, for providing me an opportunity to listen to some very interesting talks and meet some very interesting people. I appreciate that very much. My talk is going to deal with fuzzy set methods for constructing multi-criteria decision functions, particularly building fuzzy functions using information expressed in a natural language, sort of mixing words and mathematics. Perhaps first let me just say something a little bit about fuzzy sets. A fuzzy set, basically, sets are a very, very important modeling tool. We use sets to model many things. A fuzzy set provides a set in which instead of something either belonging or not belonging, there's degrees of membership. So we have something called the grade of membership, which is the degree to which an element belongs to a fuzzy set. So if I want to talk about a concept called tall, for example, and X is a person, then Fx is the degree to which X satisfies the concept tall. Now, there are many applications of fuzzy sets, particularly within the framework of actually this conference systems modeling. There's a concept called linguistic variables, where I can measure a value of a variable in terms of a word or a term. For example, it's big, it's small, it's little, and so forth. So I think this is one important area where fuzzy sets has to contribute to systems theory and system science. However, I will not talk about this. I will talk about the application of fuzzy sets in multi-criteria decision making. And particularly, I'm going to be interested in the ability to sort of model complex multi-criteria decision models, okay? Particularly trying to get how human beings have very, very complex ideas of what a multi-criteria decision function should look like. And what I'm looking at basically certain mathematical tools and models that enable you to kind of model these types of functions. So basically then, the basics of multi-criteria decision making with fuzzy sets. Here, we represent the criteria as a fuzzy subset over the set of decision alternatives. So we have a set of decision alternatives, and basically we represent the criteria then as a sort of fuzzy set, so that for the set C, Cx indicates the degree to which alternative, that should be, sorry, it's a mistake, should be alternative X satisfies criteria C. The degree to which the alternative X satisfies criteria C. And basically, what's interesting here, it's going to allow linguistic formulation of relationships between criteria, particularly using set theoretical operators to construct multi-criteria decision functions. We're going to try to model how a human being wants the decision function to look like. They'll express it in their own way, and then we're going to try to capture this model. Okay, now basically the resultant multi-criteria decision function D is itself a fuzzy set over the set of alternatives. We're going to see, so you're going to combine fuzzy sets to get another fuzzy set, which is the sort of the overall decision function associated with the particular problem. And then the selection of the preferred alternative is based upon alternative's membership grade in the decision function Z. That's sort of the basic idea here. Okay. So basically, the simplest case is the simplest linguistic expression of a multi-criteria decision problem is the following. We have the following. Satisfy criteria 1 and criteria 2 and criteria 3 and criteria 4. So now, within this framework here, we can look at this as a conjunction. Criteria 1 and criteria 2 and criteria n and so forth. This is our decision function. This is what we want to model, basically. This is a simple case. The AND is basically an intersection operation. It's an intersection operation. So basically then, the criteria satisfy criteria C1 and C2 is basically C1 intersection C2, C intersection C3, intersection Cn. So we build up this decision function this way. Now, one way, and the sort of default way to model the sort of intersection is basically using the min operator. We'll see there's other operators. So basically we take the min of the membership grade of X in each of the fuzzy sets, and that gives us the dx, the overall decision function, and then we choose X with the biggest decision, with the biggest membership in D. This is one simple case. Okay. Now, again, I'm going to just introduce a lot of things here, and I don't want to go into too much detail. But basically, we can introduce importance weighting in the multi-criteria decision problem. We can introduce importance weighting, and the key idea here is that the min operator, when you do a min operation, which is basically an ANDing operation, the bigger the argument, the less effect it has. So, for example, a 1 in the min has no effect at all. So one way of introducing importance, again, one way of introducing importance is raise the membership grade to a power indicating its importance. So when it has 0 importance, it becomes 1, and it doesn't affect the thing at all. So we have a way, and just important thing to say is that we have a way of including importance in this multi-criteria approach. We can have different importance associated with the criteria. Okay, now, there's another idea here which I just want to say a word about. It's sort of a little bit a sidetrack. I introduced the idea called anxiety in decision making. So when you have a decision function, there's a basic idea called specificity. How well the decision function points to one answer as the only answer. Okay, and this is related to the idea of anxiety. The more diverse the decision function, in some sense, the more anxiety you have in your decision. Which choice should I make? And so this kind of allows you to capture a kind of an idea of anxiety. And I think this is an interesting, make a side comment here, is that what we're trying to do is sort of measure, and model a lot of cognitive ideas, So here is one simple model of anxiety in a decision-making environment. If you have a lot of alternatives, and if it points to one alternative as the answer, it's not very anxiety-provoking. But when you have sort of diverse possible solutions, it's a little bit unclear. Have you made a mistake with the numbers and so forth? Okay, but just a side issue here. But now, I should say is the following. Perhaps in this slide we could start from the bottom up. I think it's, in retrospect, I think it's better. Notice, often people can only provide information with sort of ordinal type of information. We usually see things maybe orderly, and sometimes it's easier to do. That is, we could use linguistic values such as very high, high, medium, and so forth. So the satisfaction, instead of being a number, is a sort of an ordinal scale. And now, ordinal scales basically allow kind of min-max operations and a negation. Those are the operations you can have on an ordinal scale. Min, max, and negation. And negation is really order reversing. If you take an order and you inverse it, that's negation. So this approach here, basically, so we have this ordinal scale here, Z1, Z2, and Z3, and basically the smaller it is, the bigger it is, the more satisfaction it is. We could do it in ordinal scale, and basically we could basically model this ordinal information. So this approach doesn't necessarily require you to give specific numbers, but we could deal with a decision maker providing ordinal information. Now, basically, so what I've showed is the following then. Linguistic expression to satisfy criteria 1 and criteria 2 is basically an ANDing, a conjunction operation. Now, I can also consider the situation in which I want to satisfy criteria 1 or criteria 2 or criteria 3, so that the decision maker wants to satisfy any one of these criteria. So this is an OR, so it's C1 or C2 or C3N. And basically then it's the union of the criteria, and basically it's the max. It's the max of the membership grade of X in the overall decision function is its maximum in any one of the possible constituent criteria. Now, here I could build more complex, and this is now we begin to think about mixing words. We could think about building more complex decision functions. We could satisfy criteria 1 and criteria 2, or satisfy criteria 1 or criteria 2 and criteria 3, or satisfy criteria 4 and so forth. So the point here that I want to make here is that we can now allow people to express in a natural way what they want to satisfy. So they have these criteria. They can now express the relationship between these criteria in terms of this linguistic representation or connection here. And again, the criteria are represented as fuzzy sets, basically. So we have the ability to do this. Now, we could go beyond that. In the talk I gave here, I used the min as a max, the min for the T-norm, the intersection. But however, there's something called the T-norm. A T-norm is a sort of a generalized intersection, a generalized AND operator, logical AND operator. And basically it has the following properties. It's commutative, it's monotonic, it's associative. And number 4 is the key probability. The key, property. The key property of an AND operator is that the AND of 1 and A is A. That's what the property of an AND operator is. 1 and A is A. Okay. And so there are many examples of T-norms or AND operators, min, max, product, and so forth. So we have basically a whole family of ways of aggregating these things when we have an AND operator. So this extends our ability of modeling, okay? Similarly, generalizing the OR operator. The OR operator is what is known as a T conorm, and we can model this similarly by a class of operators. And again, they have basically the same first three properties: commutativity, monotonicity, and associativity. But the key property of an OR, or a disjunctive operator, is that the S, A, and 0 is A, okay? I mean, is A, right, exactly. And what that means, all right, so there are many examples of this. The max, these are some examples of these types of just to be T conorms of these kinds of operators, of these OR operators, okay? So we can have many forms of this decision of an ANDing of criteria, of natural ANDing of criteria. We have many ways of modeling it, many different ways of aggregating it, okay? So as I said, for the AND, we could take the min, or we could take the product of all the satisfaction to the criteria, and so forth. We could use for the OR, we could use the bounded sum, and so forth. So there's a whole family of operations we could use. And this gives us the ability to sort of learn, and what this provides us is a facility then, using families of T-norms enable us to parameterize representation of multi-criteria decision functions. So we have this whole family which we could sometimes use with one parameter, and we can model different, take data, persons, here's the satisfactions to the different alternatives, here's the overall satisfaction, how are we combining them? We can learn that, we have the ability to learn that. Okay. And we can generalize importance weighting. I don't want to get too much, this gets too much to digest in a talk, and it's too much for me to say. But in other words, if we have different types of models for the AND or the OR, we have different ways of introducing importance and so forth. But we can include importances. Okay, same thing for the OR. All right, now, basically, just let me say something about the AND and the OR operators in general. The OR operator, the ANDing operator, then basically, if you have any one of the constituents has a 0 satisfaction, the overall satisfaction is 0. That's clear. So, imperative of a class of decision functions of the ANDing is that all imperatives must be satisfied. All criteria must be satisfied. Another feature of this kind of ANDing operation is that as you add more and more criteria, your satisfaction goes down. So an ANDing is really, you start off with everything possible, and basically as you add criteria, you take away possibilities. This is sort of like logic in some sense. Now, on the other hand, an ORing operator is slightly different. If the membership grade of some of the one criteria has one satisfaction of 1, then the overall satisfaction is 1, okay? So the imperative of the sort of the ORing is at least one criteria must be satisfied, okay? Now, I spoke about two types of basically aggregation of multi-criteria. One class being sort of conjunctive, which is an ANDing. At the other extreme is the ORing, which is basically the disjunctive type operation, an OR. But in between is the mean types of aggregation. So in many cases, we see the mean as being we take the average of the criteria satisfactions. Okay, so now I want to look at sort of mean aggregation operators. Mean aggregation operators. So basically, a mean operator aggregates a number of objects, a number of scores, a number of satisfactions to the criteria. It's commutative, that means the order doesn't matter. It's monotonic, that means as I increase the value, it increases. Now, the key feature of the averaging operator or the mean operator is bounded. It's bounded in the sense that the aggregation of A1 through AM is greater than or equal to min and less than or equal to max. As a matter of fact, the max and the min are your extreme objects, okay? It also has another important feature called item potency. Item potency is the feature that if you take the aggregation of all the A's, everything is A, it comes out to be A. It's an average. It's what we know as the normal average, basically, but of course, we'll see other examples. Now, there are many examples, again, many examples of mean operators, which is the max, the min, the median, the average. we'll talk about the hour operators, which is something, and the Choquet aggregation operators. So there's a large class of ways of modeling the mean, which is an important way of combining multi-criteria. And so I want to look at some of these, okay? Now, what I'm particularly going to talk about, the ordered weighted averaging operator, which I introduced, okay? Now, the ordered weighted averaging operator, by the way, it generalizes, those of you who are familiar with the book, okay, let me explain it to you, and it'll be clear in a minute, okay? If I have a mapping of a number of elements, A1 through AN, I get the average is the WJ times BJ, WJ times BJ, where here, BJ is the jth largest of the AJ. So I take my arguments and I order them. And then I multiply them by a weight, which are basically lie in the unit interval and sum to 1. But these weights are not associated directly with the AIs. The weight is associated with the position. It's an ordered position. Okay, so the essential feature of the hour operator is there's a reordering operation of the arguments, and also weights are not associated directly with argument, but with ordered position of the arguments. We kind of order the arguments and then we weigh them. And the weights determine the type of aggregation you're going to do. Okay. Now, you'll see what happens is there was a very famous book by Lewis and Raphael, which is a beautiful book on decision making, and they give you a whole family of decision functions. And you see, I'm able to capture all these decision functions in a kind of one way. Okay, so if I have my weights are W1 through Wn, these are called the weighting vector. I have my arguments, which are ordered. Again, the arguments are ordered. It doesn't matter. Okay, and I take the sort of the aggregation of these ordered arguments. This slide will just go over a little bit here. All right, so the form of the aggregation is dependent upon the weighting vector used. Depends on the weighting vector used. The aggregation is parameterized by W. So here's what I mean. If the weighting vector is such that W1, if you look at this as a vector, where W1 is the top element, W2 and so forth, going downward, if W1 equals 1, we end up with the max operator. If Wn equals 1, we end up with the min operator. If Wj, if they're all the same, we end up with the ordinary average. So here we've got all these operators. We'll see other ones that come into play shortly. So we have a sort of parameterized way of introducing the aggregation of multiple values or multiple criteria in the case of this case. It doesn't necessarily have to be in criteria. It could be information. Now, there's something which I introduced called the attitudinal character of the hour vector. The attitudinal character is basically if I take the weights and I take some sort of average of some sort of function of the weights, I basically get some sort of characterization of the weights, which lie in the unit interval. And if the characterization is 1, I'm doing a kind of an ORing. If the aggregation is 0.5, I'm sort of in the middle, and if it's 0, I'm doing a kind of an ANDing. Okay, so we have some sort of characterization of the kind of aggregation. Okay, so as I say, the attitudinal character near 1 indicates a bias toward larger values in the argument. An attitudinal character near 0 indicates a kind of bias towards smaller values, and an aggregation of 0.5 is an indication of neutrality. Now, to some extent, when you use this stuff in combining probability and stuff like that, this is a sort of a measure of your optimism. Basically, when you have a 1, you're very optimistic. When you have a 0, you're kind of very, very pessimistic. Okay, so it can provide that kind of also information, or allowing a person to include how optimistic they want to be, or how pessimistic they want to be, or how and-like or or-like they want to be. They're just giving the parameter itself. Okay. Another measure here is the measure of dispersion of the weights. The measure of dispersion of the weights, basically, in some cases, I could use only one weight. There's, for example, the and is only one weight, and the or is only one weight. I could put one weight in the middle, Wn over 2 equal 1. And so this is the dispersion, how dispersed my weights are. I prefer, of course, to use all the weights, but I can't get every different types of aggregation using all the weights. Okay. Now, there's some interesting further notable examples of this kind of operator here. For example, I could get the median. Okay, I could get the median. If n is odd and wn over 2, wn plus 1 over 2 is equal to 1, I get the median. I could get the kth best. I could get what I call the Olympic average. The Olympic average came about, many years ago, not that many years ago, but, in the Olympics, when you used to have these events like diving and where you had judges who used to take the score and combine the score, what they used to generally do, because the Americans used to vote against the Russians, and the Russians used to vote against the Americans, what they used to do is sort of take out the two n values, the biggest value and the smallest value, and then take the average of the two. This, what I call the Olympic value, I could do that. Also, there's the Horowitz aggregation operator. The Horowitz aggregation operator basically assigns a degree of alpha, which is a degree to the best solution, and a degree of 1 minus alpha to the worst solution, and 0 to the ones, and it characterizes those. Again, these basically model, again, in that Lewis and Rafer book, there's a whole lot of decision functions, and this kind of captures all those decision functions in one sort of general way. Okay. So the hour operators provide a whole family of functions for the construction of mean-like multi-criteria decision functions. Okay, I think I have a few more minutes. Okay. Now, the question is, how do we get this weighting vector? How do we get this weighting vector? Again, I'm trying to model a human being, so it's really the human decision, in many cases, the human decision maker's choice. So one choice is a direct choice of weights. Here are the weights, this is what I'm going to do. Another example is some notable types of aggregations that I showed before, the max, the min, and so forth, okay? I can learn the weights from data. I could use characterizing features, or I could use linguistic specifications. And let me show you what I mean by these. Well, let me just say learning, I don't want to get too much involved in learning. Basically, you have data. You have the data, you say, here's the arguments, and here's the results. Let me learn the weights so that I could obtain model lists. This is a kind of classic learning, and we have a procedure for doing that. We could use characterizing features. That is, I could say the degree of oddness I want, or degree of attitudinal character I want between 0 and 1. Say I want to be somewhat and-like, or somewhat all-like, and so forth. And then I could sort of obtain the ways to match that using my attitudinal character function. There's a method which was suggested by Michael Hagen, which says we specify a degree, an attitudinal character, and when we determine the weights to maximize the dispersion, so this is a maximum entropy type of thing. We have, this is basically, this is the degree of sort of dispersion, the maximum, and then we have a classic mathematical programming problem that the attitudinal character equals alpha, the weights sum to 1, they're all greater than 0. Another one, I think an interesting one, is we can have a linguistic specification of the weights. And this is, I think, interesting here. So what I could do now is, at one extreme is and the other extreme is or. We handle those things. In between the things like most, many, about half, I want almost all of the criteria, I want some of the criteria, and so forth. So what I could do, linguistically specify the aggregation imperative. Translate the linguistic imperative into a fuzzy set, and using a fuzzy set, determine the hour weights. And let me just show you what I mean here. So in other words, what I call quantifier-guided aggregation of criteria. I have a bunch of criteria. At one extreme, D, the minimum, the decision function is that the minimum, all criteria must be satisfied. The other extreme is at least one criteria must be satisfied. Another extreme is, I use the word quantifier criteria must be satisfied. That is, most criteria must be satisfied. Almost all criteria must be satisfied. Some of the criteria, at least half of the criteria, and so forth. These must be what we call monotonic, but I don't want to get into that. And so what happens is that basically then I can represent a linguistic quantifier as a fuzzy set, or represent a quantifier as a fuzzy set. And we represent a quantifier as a fuzzy set. And here's we're talking about mixing words and mathematics. I model a quantifier as a fuzzy set. So for each degree, QR, which is the sort of proportion satisfied, QR indicates the degree to which this proportion satisfies the quantifier. Okay, basically. So I can model a quantifier. And the next slide we see, this is sort of what a quantifier looks like. Quantifier looks like the degree to which this R proportion satisfies the quantifier. Now, let me get this thing over here. Just do this fast. I guess I don't have time, but from this thing I could get the weights. There's a weight, I could just get the weights right off here from this quantifier. So here I'm using some sort of quantified expression. All right, I think I'll stop here because I'm running out of time. I don't want to go over. So I have this. So I'm able to linguistically express the proportion of the criteria I want to satisfy, get the weights, the model of it, and so forth. Okay. I think that's the end. Thank you very much.